All right, welcome to today's nutrient removal webinar cohort. We will be talking about chemical removal of phosphorus at wastewater treatment plants, and I'm cheating on this towards the end. We're actually going to be talking about using chemicals, but the chemicals themselves aren't removing phosphorus, but they're preventing phosphorus from re-releasing later on in your process. So kind of some innovative ideas I've seen in other states and possibly applicable to plants here in Kansas. As I mentioned, if you are with multiple people, or if your screen isn't showing your name, change your screen. So I get the, I need your OP number and name if there's people other than you on the call today. So we'll go ahead and get going. I'd like
Morning.
to
Good morning,
begin with
Shirley. Hi.
the takeaways. Here, and somebody's coming through on audio. So to begin with, let's talk about takeaways. So the first one is that chemicals can be used to minimize phosphorus discharges. So unlike your nitrogen removal, you have the ability to use chemicals to meet your permit limits. So it's another tool in your toolbox should you need it in the future. It's also very important to understand those flows with phosphorus within your plants because unlike nitrogen, you basically just shuffle phosphorus around. It never leaves your plant as a gas like nitrogen does when you denitrify. So that is something to keep in mind, that you can do a really good job biologically and then lose it all back and it goes back into your plant's effluent. Additionally, the type of chemical, location, and timing of dose will be site dependent. So, like many things in wastewater, your wastewater treatment process is different than one down the road from you. So, keep in mind that what works at a neighboring community may not work at yours. You have different influent, you have different processes, you have different water qualities. So, you'll need to do your homework and some iteration to figure out what works well at your facility. And I'll talk about some of that effort we've done in previous years under my work with KDHE. So another takeaway here is phosphorus is different than nitrogen. So you convert your ammonia into nitrates and then you denitrify and then you get into gas. So that denitrification step is not something that there's a comparable step with phosphorus. You get rid of nitrogen in your plant and it stays out of solution because it is actually gone from the liquid and solid streams. So when you're looking at phosphorus removal, keep in mind that it's going to leave the plant in your sludge, and that's what you're shooting for here with biological or chemical phosphorus removal, that you're taking phosphorus out of solution and putting it into the solids, and then it's dealt with in your solid stream. You can also have it go in total suspended solids. So if you're doing the good conversion into the biosolids of your plant or you're dosing chemical, you still have to have that liquid solid separation step be good. Most facilities of yours that I've been to do a real good job, and you have relatively low total suspended solids. But if you, for some reason, have a clarifier upset, where you don't get settling, you can potentially violate your phosphorus permit limits through high total suspended solids, even if your biology and chemistry is working well. To keep in mind, you also want to look at in-plant phosphorus recycling. And recycling maybe isn't the right word. That tends to be thought of as a societal good. But the idea is that you can remove phosphorus only to have it get back into your liquid stream process. Again, we won't go into all of the details, but in biological phosphorus removal, you're taking what is typically orthophosphate and moving it from dissolved in the water into the biology, which is then removed in your solid stream. All of the phosphorus that enters your plant is leaving it. That's kind of just basic fundamental physical principle. We can't create or destroy matters. So the phosphorus is coming into your plant. It's leaving in the solids, in biosolids or dissolved form. Plus, you're going to have a little bit of phosphorus leaving with, your 2, 4, or 5 milligram per liter of TSS that is going out into your effluent. Um, Once your phosphorus is in solids, it can return to dissolved form and leave an effluent. So chemicals might be a lot more effective or economic if used in the places where you're getting that phosphorus release. And we'll talk about that towards the end of today. I wanted to cover a little bit of basic phosphorus chemistry here. So this diagram here on the right side of the slide is a basic orthophosphate. Anything dissolved in water as a salt, has to have equal charges. So they're showing the sodium Na plus ions. Could be something else. It could be a single calcium, which is a 2 plus ion, to offset the negative charge of the orthophosphate. Almost all of the phosphorus hitting your plant is in this form. That is the way it leaves our bodies. That is the way it is in our food preservatives. That is what you're going to primarily see at your facility. There are some components of phosphorus within solids that are hitting your plant from human waste and just other particulates. So, for example, most of the soils in Kansas fairly rich. If you get silt or clay particles within your collection system, there will be some degree of phosphorus there, but the vast majority is going to be in this orthophosphate form. Notably, back in the day, I remember seeing articles as a kid in the 90s, that there were changes to dishwasher soap and laundry soap as detergents went from having phosphorus to having no phosphates in them. So you see up here again on the upper right corner, this is the phosphorus molecule. It looks like the end of a detergent. So you have, instead of phosphorus now, you often have sulfur atoms, but you're doing the same thing. So the right side here is reacting with the water, and then this is reacting with oils. But that is what oil looks like to some degree. It's typically long chains of hydrogen and carbon out. And so this has affinity for oil, dirt. Almost all dirt, at least from human bodies, has oil attached. And it allows it to pull off into the water in the hydrophilic, so water-loving side of the molecule. So my point with this slide is that when you are trying to react with this up here, you want to have water that's relatively clear of similar looking compounds because they're going to react often and interfere with the desired reaction. You want your chemicals to interact with this molecule, not this one. If there's a lot of these type of detergent molecules in your water, you will get typically less efficient reaction because some of the chemical that you're applying to remove this is actually going to be interacting with these particles. An atom can only, a chemical can only react with a chemical, and then it will be used up. So if you interact with this, bind it, then this orthophosphate will still be floating around in solution. So I want to talk about some of the phosphorus binding chemicals out there. So this is the most common way that chemicals are used to keep phosphorus out of surface water discharges. But as I'll talk about at the end, it's not the only way necessarily. So what we have are typically what are called metal salts. So what the heck does this mean? Try and explain that a little bit. So many metals, which are dissolved in a salt solution, will have affinity for orthophosphate. And there's a lot of metals that are out there, and there's just a few that are used for binding orthophosphate in wastewater. So a salt is something that will dissolve in water, and it will contain both cations, which are positively charged, and anions, which are negatively charged. The charges are going to balance out to zero. So sodium chloride, sodium's +1 charge, chloride is -1. That's a salt. It'll dissolve in solution. Many salts dissolve in water, but some really kind of don't. So those are ones you would want to avoid
Fucking
within the wastewater
unlivable.
treatment
Like how fucking
processes because you're dealing with the liquid streams.
God.
Um, so certain cations and anions are going to be more attracted to each other. So sodium likes chloride, but sodium may also like other molecules out there floating around in the water. And when you're dissolved in liquid, some of those interactions will actually form what are called precipitates. And that is what we're going for when we're adding chemical to wastewater streams to remove orthophosphate. That in order to remove it, we want to precipitate out
Hello.
orthophosphate
Yeah.
reacted with salt. So that's exactly what we're doing with the metal salts in that are being added. And we'll talk about some of the common ones that are used. So what is a metal? Here on the periodic table, there's a lot of metals. Now, obviously, we're not going to use many of these that you're testing as contaminants. We're not going to use lead. I don't know if it binds with orthophosphate, probably to some degree. We also aren't going to use things like gold and platinum. They may work, I don't know. But you're not going to get very far in your budgetary ask when you ask for gold chloride or whatever that would be. So what we're typically using are some of the molecules over here on some of the rare earths, and then iron, which is Fe, kind of here in the middle, and aluminum is very commonly used as well, and that is up here by silicone. So the chemistry we're looking at here is the common kind of commodity type chemicals are ferric chloride and aluminum sulfate. These are probably the most commonly used one. Ferric chloride is dissolved, and the reaction that we care about with regards to removing phosphorus is the 3 plus acts with the 3 minus PO4, and then it kind of combines for FePO4, so ferric phosphate. And this is not soluble in water and will precipitate out and be able to be removed in your solid stream. So typically that's going to be your clarifier at most plants. Here is the more complete total reaction. Again, we have to follow all of the atoms that are in this have to come out somewhere else. Um, Keep an eye on this one because that's important. We'll talk about it later on in today. So the ferric chloride and aluminum sulfate, basically the same type of reaction going on. So the aluminum phosphate is very insoluble in water and it will precipitate out. Here's a larger reaction there. Again, I would pull out this 3H2SO4. That's important as far as plant operations goes. Ferric sulfate, same basic idea. I think you're probably getting the idea there. Now, those of you who have chemical vendors, they'd be happy to sell you something as well, and it may work better than some of these. If you're really looking at like full-time or significant purchases, I would strongly encourage you to contact them. They will probably bring out a polyaluminum chloride. Um, and there's a lot of these. They're often bespoke to a certain chemical company. It's going to have very similar chemistry to alum. It may be more efficient for some reason or another, more cost effective, easier to deal with. Maybe you need to dose less of it in total. And then there's rare earth, which are typically going to be cerium and lanthanum chloride. There's vast kind of lagoons of this in China that's sort of a waste product from other metals processing. So there's a couple, three companies, to my knowledge, that will sell this into the wastewater industry. It typically reacts very well with orthophosphate. The advantage of it, according to the sales reps, and always do your own due diligence on this, is that it binds less water. So you're actually kind of making more of a solid rather than a gel type substance that's being dropped out of solution. So just a little bit on that. Um, there's a couple different ways to approach chemical addition in wastewater treatment facilities, and I'm thinking that we're going to eventually land for probably most plants on something like the second of these. Um, so the first thing you can do is to just run chemical all the time and meet your phosphorus limit. This is going to be necessary at wastewater treatment plants once you get much below 1 milligram per liter as your limit, especially if it's a hard monthly limit rather than like a rolling average, like most plants here in Kansas have. Um, and it will often be combined with tertiary filtration. So you may actually dose after clarifiers and then add some sort of a disc filter or something like that to remove the solids generated by the chemical dosing. Um, there are some plants that it probably makes sense to use this as a stopgap. If you have an older facility and you're planning to do some upgrades, but it's not going to happen in time to meet a permit limit, you could add chemical until you reach the point where then you do a full-scale biological nutrient removal facility. That could make a lot of sense. Again, do your jar testing. You want to make sure that you're getting the right chemical and one that is economic for your operations. What I think we'll end up seeing, as long as total phosphorus limits are around that 1 milligram per liter, is that most facilities are going to have some sort of dosing infrastructure put in, but they won't use it most of the time or use it only, half the time. Most likely for plants based on how they've been performing here in Kansas, this is going to be the summertime. We tend to see higher phosphorus discharges then. Um, it may also be for some communities related to industrial production. We'll see some inconsistent phosphorus loadings at some facilities. Um, but most facilities are going to want to try to get their biological phosphorus removal working well, if they can, rather than relying on this. If you are looking at chemicals, definitely look at jar testing. I've done jar tests for a lot of facilities, I think maybe 35-ish here in the state. If you've come on since then or have lost it, I do have all of those reports. I can share them with you. Um, uh, Keeping in mind that, if you had significant changes in your collection system, the results may not be very valid anymore. But you do want to jar test if you're looking at using chemicals. And the reason is that jar testing kind of answers a lot of questions that can't be answered in any other way, at least that I've seen. Every system is going to have different source waters, industries, types of commercial establishments, collection systems. One where the water is fresh versus one that has, multiple lift stations. Things are going to react differently because the chemistry is different. Likewise, you have different wastewater processes. So one of the most advanced treatment plants is here in Dodge City. It's membrane bioreactor. That's going to respond differently to chemical addition than the overflow at the city of Bueller's plant, which probably dates to the early 80s. It's two-rotor oxidation ditch. Do the diligence there. I have found in jar testing and in some real world experience that there are some chemicals that won't work at some plants. So you don't just make that assumption. And some chemicals are far less economically efficient. So jar testing looks like this. This is the setup I used to run around with. I would run 12 tests at a time. Um, Used to get a referral from KDHE. If you want a jar test from me, I can probably do it again. I need to get some supplies. But your chemical vendor may be actually a better source because they can touch on more. You do want to be careful. So as I mentioned, any atom that we're bringing into the system is going to be leaving your system. Ferric chloride increases the chloride leaving your plant. Aluminum sulfate and ferric sulfate will increase the sulfate leaving your plant. Throughout Kansas, we have a lot of stream impairments for chloride and or sulfate. So if you're looking at adding a metal salt, that is something to consider, especially if your testing is showing that you're a cause of the impairment, because you're going to increase the loading of the chloride or the sulfate respectively. Um, So here's a little bit more. So this is saline as influent. And you can see that it kind of ferric chloride does a lot for cleaning up the influent. It precipitates a lot of the nasty stuff that's in their flat collection system, um, and that's what it looks like. The jar testing should test in multiple locations. Your plant layout will kind of drive this, but there are multiple locations that are useful for chemical addition. And actually, in the real world, evidence often will say that dosing in two locations is going to be more economically effective than a single location. That's going to matter a lot if you're spending $100,000 or $4,000 on chemical. Any efficiency you gain on very low usage is going to be offset by having additional infrastructure and upkeep in order to dose in multiple locations. But generally, you're going to want to have a combination of good mixing. You can see all these chemical additions from this WEF document. And then you need to have solids removal afterwards. So this is why at most facilities, your last feasible dosing location is going to be before your secondary clarifier. This is showing a tertiary clarifier or something like a sand filter where you can add chemicals there before leaving plant effluent. But if you don't have this tertiary solids removal, you have to do it. The latest spot can be before your secondary clarifier. So what have we learned here? From the jar testing I did in previous years, incoming phosphorus concentration, that was part of the work I was doing to estimate, the cost of removal. It is a problem in some facilities where what you're getting from the collection system is peaky, it's inconsistent. That's going to make both chemical and biological phosphorus removal tricky. So additional process monitoring or maybe source control is useful there. And then when you're running a lot of samples in a day, I actually don't think Hawk makes these anymore, but there were ampules. They just fill up and then you run a test in them. You could be quite productive at that point. What we saw was that generally dosing before the final clarifier had a lot lower dosage rate to get to 1 milligram per liter than if you were dosing somewhere near the headworks with the influent. Again, that's going back to that detergent slide to a large degree, that there's other stuff to bind with in the influent. And once a lot of that has been removed past the headworks, past the aeration tanks, then you get more efficient chemical dosing. Part of this effort, we looked at having the cost per customer per month. So not per person, but per connection. The lowest was 28 cents per customer. That's something you probably would really consider if your plant's otherwise working well. The other one's at 8.44. That is beginning to get to the cost of a new facility on a state revolving loan fund type of system. So this jar testing really revealed a lot. Likewise, if you did have a really high number here, that would be like call your chemical vendor, see if you can get a pack or test out the rare earths. It's worth doing more homework on that. At the 28 cents per customer, you're probably not going to find a whole lot of savings because there's not a whole lot of cost where you're starting from. Um, we also found that I wanted to kind of get some takeaways here. So this is at Derby. This is the actual test results. We saw that dosing their influent was about a little over $400,000, and that was with ferrous sulfate. I believe the Ark River there has a chloride impairment, so we didn't use that. So you could get away with it here for ferric sulfate for the influent and get to low levels. Dosing alum in the influent didn't really work. You saw that it would peter out at about 2 milligrams per liter, despite how much alum you wanted to add. Then we saw that ferrous sulfate before the final clarifiers got you there. It got you levels under 0.5 milligram per liter if you need it. at a cost of about $100,000 a year. And then alum was about 100, it was about $20,000 more. It got you to about the same levels. So what does that mean for Derby in this case? It means they have options. Alum would work, ferrous sulfate would work. They'd want to figure out, health and safety issues. $20,000 isn't going to break the bank on a system that size. So they immediately start looking at, other impacts to their processes, being that they're pretty comparable cost. Um, at Hayesville, we saw this no compliance no matter what. Dosing influent with alum wasn't very effective. Likewise, the influent dosing at Hayesville, similarly. Um, we saw that it worked, ferric chloride before the final clarifiers worked. But you saw that the curve kind of levels off, and the values we never got really below 0.5 mg per liter. So it works if your limit is 1 mg per liter, but if you need to get to 0.5 mg per liter, you need to find something else. Likewise, we saw about half the cost with alum there at Hayesville, but we weren't able to really get below 0.5 mg per liter with the jar test. So for the time being, Hayesville has options dosing before the final clarifier if need be to meet their limit. Want to talk a little bit about the dosing infrastructure that you need. Most of the pumps are going to look something like this, a peristaltic pump. It basically is kind of a cam that rotates around and squeezes a actual portion of liquid through it as it rotates around. So it does pulse. Many of you are going to be familiar with this from other locations in your plant. They're pretty cheap pumps. I have had mixed reviews. Some people find that they don't last very long. Others, they are reliable. I don't know the difference. I haven't never really explored it, but you may want to call around to see what is working well for them. Um, for if you have a large facility, you are likely going to wind up with a bulk storage and delivery. This may be an issue if you're trying to take a semi-load of liquid. Do you have the infrastructure at your facility to get a semi in and out safely? For seasonal dosing and small plants, you're probably going to end up with a barrel or tote type of system, and then you put this pump on top of them. Um, uh, if you have to dose in the winter, you're going to have to think about, this is one more thing that can freeze up, that can gel. So that would be a consideration. You'll likely end up with heat trace unless if you're doing this entirely inside. You may have to build kind of a dog shack for the tote and barrels. Um, some plants I've found are actually have empty conduit that you can run lines in, which would help with the winter issues. And this is all the more reason to optimize for BioP in the winter. I can think of several plants here in Kansas that can probably get away with just putting the toad out in late April and bringing it in late October, dosing as needed, where they wouldn't need to worry about this winter type infrastructure. So it's one more thing to keep in mind when you're looking at this. Another thing is that, especially with the alum and ferric addition, is that you're going to have more sludge production if you're adding chemical. Because, I mean, in one degree, you're just taking compounds out of solution and putting them into solids, so the mass is going to be higher. But the metal salts, especially, are going to entrain a lot of extra water, in addition to the phosphorus they're removing. So you might have 8 parts of water per 1 part of phosphorus. That will increase your sludge production. Um, I've had operators ask me, and I've not ever found a straight answer. But kind of the WEF type of literature out there says about a 25% increase is what you should plan for. Some facilities, that's not going to be an issue. Some of them are going to quickly have issues with, biosolids operations. So, if you are constrained on your digester capacity, if you're constrained on your belt filter press capacity. This is something to really have an eye on. Work in slowly. It might be a case for the rare earth where there is less water entrained and you might get less sludge production. So this is all the more reason before you have your limit to be testing various options for you. Um, there are going to also likely be impacts on your dewatering operations. We're changing the chemistry of the water and the sludge here. You may see that you need to switch polymers. You may see more polymer demand, less polymer demand, but just be prepared that your belt filter press operation, your centrifuge operation may be impacted, and you'll have to make adjustments to it. There are challenges with chemical addition. One of those I was highlighting the other atoms that come along for the ride when you're dosing ferric chloride, aluminum sulfate, and other compounds. In addition to the chloride and sulfate issue, we actually are having hydrochloric acid here and sulfuric acid with the sulfate compounds. So, that means your pH is going to drop, your alkalinity is going to drop. The alkalinity available for nitrification is also going to decline because your alkalinity in your return activated sludge is going to decline when you're adding acids to your process. I don't think this will generally be much of a problem for most of the source waters in Kansas, but if you do have either reverse osmosis or a softening system at your drinking water supply, this might be a concern for you. Something to keep an eye on when you're adding chemistry to your plant. And then there's just like logistics. So here's a headworks. Medicine Lodge, maybe. Here's, the plant is often, towering out of the floodplain like this one is. This is also Medicine Lodge. So if you're having to put chemical infrastructure, that's a lot of exposed piping that, is going to have to be heat traced. And then I want to cover here. So this is UV lights. The iron compounds often will lead to staining on the quartz on the outside of the UV lights. So if you have staining there, then your UV light transmittance, I think, is the right term for that. That's not something I deal with a lot. But some of that UV light, that UV radiation is going to be blocked by the iron that has bound up with the quartz and stained it. So that is something you'll have to clean more, maybe replace more, or possibly avoid by not using an iron compound there. Chemical storage is often a space issue, and then an access issue if you're taking bulk storage. Obviously, the cost too is something to keep in mind, and then that UV lamp cleaning. It's also the reality that if you're putting in chemical in a plant that wasn't designed for chemical, you'll often start to notice that really fast. So this is Kingman, I believe. You can add, very common to add some level of chemical in the headworks, which would be dosing there. And then a splitter box before the clarifier. So, that's 50, 70 feet. But it's in a roadway, so you kind of have to think through how to route things there. This is Ellenwood. It's a two-cell SBR. Some SBRs have infrastructure to add chemical and dose it appropriately. This one does not. Could be added at extra cost. So that's really only option is adding it here at the wet well. Well, it's just conveniently by building, so having a tote in there isn't that much of a problem. Then you have plants that are kind of split, where you have parallel operations. This is Norton. You can add chemical to the headworks, which if that's your only dosing point, that would be worked pretty well. Unfortunately, that tends to not be the most cost effective dosing point. You add a lot more chemical than you do if you add it before the clarifiers. But this is a Schreiber basin. Somewhere in this outside tank is the inlet to the clarifier. Um, and this arm here and this one, it's basically two identical systems. They move around. So you're going to have to figure out how to get a tube to this tank or possibly all the way down to the inlet to the clarifier so you get proper mixing. Possible, but it becomes a lot more complicated there. This is the Aeromod design. We have a lot of them, and the new ones are that I'm seeing are having this infrastructure installed from the beginning. This is Maze's plant. They have an offline Aeromod that's older, and then they have a newer plant to the south of it. Um, so they more or less have two parallel plants. So you could dose in the headworts or what they call typically the BioP basin. Or, if you want to get it probably more efficient, it's going to be on the outside of the clarifiers before the clarifier baskets. I think you can start to go crazy with this. Charlie from It's Always Sunny in Philadelphia with Pepe Silva. So here's the logistics here in Maze. You dose before the clarifier baskets here, so somewhere upstream of them. And then this is past kind of all the headworks in there. So here is Maze. Here's additional jar testing from Maze. Doing ferric chloride to influent, not effective. Alum to influent again. And then we see like, oh, well, here's ferric chloride before the final clarifiers, which is, where I would generally guess would be most cost efficient, but it may not even work. We are getting levels right at what would be what your target is at 1 milligram per liter. So relatively cost effective for the size of town there, but may not actually work to have compliance all the time. Where alum was actually cheaper, and it does seem to get more towards zero point 0.7 rather than 1 at the low end of the higher dosing of testing. So you may also want to be considering tertiary treatment. So here's plant effluent leaving. Somewhere in here, you would dose chemical, and then there would be another step, in which case you would probably end up with a disc filter type of system. That seems to be what is going in for tertiary treatment these days. Um, so you may also have a sand filter. I haven't seen a new one lately, but there are a few sand filters out there. Possibly also a polishing pond. I think that might be flirting with disaster because you'd have a lot of solids settling in it, and then you lose pond capacity. Possibly to see release of phosphorus there as well. Um, so this is a discussion we have with operators sometimes about, is there a benefit besides phosphorus for adding tertiary treatment? So, you may not have the best total suspended solids performance, which that would be a good reason to have it, or you may have reuse. It seems more and more systems with reuse are getting some sort of a tertiary treatment. It keeps the solids out of downstream irrigation systems and things like that, which can be pretty helpful. Another thing you may want to consider is flow pacing. You don't have the same flow in and out of your plant all the time. Um, this would be especially advised if you're using a lot of chemical or it's year round. You may also have a sequencing batch reactor that would make a lot more sense to have that. Um, that does require additional kind of controls and probably more expensive dosing infrastructure as well. But you'd see savings on chemical usage and also, possibly better compliance. you'd be less likely to overdose chemical and have a pH violation or loss of uh, nitrification due to overdosing. There are online phosphate analyzers available that you can purchase, uh, which can tie into the dosing system. Um, I've only seen a few of these, and they tend to be at plants that have very, very low phosphorus limits, but it is out there for you. Um, Want to talk about a few cautionary tales. This Edgerton, they have a Schreiber system, and they're in Hillsdale Lake, so they're under a lot of pressure to preserve surface water quality. Um, there, at the time I visited, the permit goal was zero point 0.3 milligrams per liter with a limit that was a little bit higher than that. This was a relatively new plant. They had dosing infrastructure just really to get to zero point 0.5 reliably. You're almost certainly going to have chemical addition. They met the goal with alum dosing. It worked really well, and then it stopped working. Don't know why. And I went out and visited. So here's kind of their compliance. It kind of went all over the map there for a while. Um, and we're like, okay, let's figure out what the problem is. I don't know that I can tell you we actually got an answer, but it was a fun exercise to go through. So one of them was like, okay, the chemical line dosed a pipe that was underground, possibly it's leaking. You would think that would come up at some point, but possibly not. Um, that's really the type of solution we wanted. Like, there's just something broken here. Pull it out, replace it, go on with your life. Possibly there were changes to source water. This is a growing area. Maybe a higher fraction was getting a rural water supply that added orthophosphate as part of corrosion control, something like that. Um, we also were considering there's it's kind of the area where they have the rail to truck infrastructure, a lot of warehouses. Possibly there was some chemical in the collection system being used that was interfering with the alum dosing. We have some more chemical theories. Possibly it was just the alum wasn't really good alum. Maybe it's weaker concentration, so you're not seeing the response you would hope. We also considering maybe there's a new industrial discharger that's increasing orthophosphate or having some sort of interference. Staff was unaware of any at that point. Possibly the strength of the flow is different, but we couldn't really find evidence of that. Other DMR was more or less the same. So we tested everything we test, which was alum, ferric chloride, ferric sulfate. And then I also tested alum from that big tank that Edgerton have. What did I learn from it? Bad chemical wasn't it. My alum and their alum basically got to the same values. We also tested higher doses of alum, like, well, maybe if you just turn up the knob a little bit, it will get you back into compliance. And we got one of those flatlining situations where you can add more chemical and you don't get any more response. We figured that a leak was an unlikely explanation of the cause because I was getting similar values with my alum to their alum, so it seems like it was probably getting in there. Um, we also found that with the chemicals that we tested, reaching that permit goal of zero point 0.3 was going to be difficult with any of them. So more exploration might be needed, something proprietary, maybe one of those rare earth, maybe a pack, maybe additional filtration after that as well. So what do you draw from that? Chemical addition is not entirely reliable. It's like everything else, things can go wrong with it. So you need to have a plan in case if it does fail. Because again, if you're using it all the time or you're using it seasonally, it is required for compliance in that point. So figure out how to diagnose, have some plans of action. What if you need to switch chemicals? Uh, can you just put them in there? Do you need to clean out the lines? Do you need to replace your pump? Do you need to possibly move your dosing location? Um, so just keep in mind that there are failure points for chemical addition. They're just different. So mechanical, chemical, supplier issues could all be that. And this is also like I was there in 2018. And we had all the supply chains with COVID. That's another thing to think about, which wasn't really on the radar at that point. So things to keep in mind. I also am going to briefly touch on Dodge City. They have a really well-performing plant. It's maybe the most advanced in Kansas, so there could be some arguments we could have about that. It's a membrane bioreactor, puts out really nice effluent. It is biological nutrient removal going on at the facility, but it was working really well except for 1 month. And I believe they have a rolling average like everybody else. But their result was 6.4 milligrams per liter for the month of December. And if you do a rolling average, it's really great if you have something high, but if you have something really high, it stays with you for the next 11 months. And so plant staff is like, we don't want this to happen again. What can we do? How do we plan for it? So they asked me out. They wanted a suitable dosing location. They wanted information on the effectiveness of chemicals. And they wanted to avoid that 6.4. So if they're doing process control testing and they see their numbers getting up to 2 or 3, I don't know what the number actually would be, then they're going to start dosing chemical to bring that down to avoid that high number that goes on the annual rolling average. What we found here is that for Dodge City, they have BNR that's very reliable, except for occasionally it's not. Um, the economics are very much not the driver of decision making. If they have to buy a total chemical, it doesn't matter if it's twice the cost if it sits there for 5 years. They also have different infrastructure that they need to protect. So they have membranes. Is the membrane manufacturer cool with you using all of these different chemicals? That's something to definitely do your research on. We found that ferric and alum both worked. So at that point, it was like, what works best for you? The plant also understood what kind of dosing it was needed. So if they needed to remove 1 milligram per liter of phosphorus of a daily flow, they would need to dose 63 gallons of alum or 100 gallons of ferric. So with this is actionable information for them. Um, uh, we also talked about process control monitoring. That orthopede upset is not normal, but you need a system to be able to look at that. Another thing is that these membrane plants have very high recirculation rates. So if you actually dose the system, you're going to want to pay attention to things like pH, alkalinity, and things like that if you are actively dosing, because you could upset other processes in the plant. Finally, I want to move to chemicals and solids handling. Why do I want to talk about this? The best use of chemical to prevent phosphorus, high phosphorus levels in your discharge may not be in the activated sludge portion of that plant. So that diagram I showed you with all the dosing locations, that may not be where you actually want to dose. We have a lot of facilities that have pretty high flow rates from decant operation, belt press operation, centrifuge, etc. Perhaps coming from drying beds. Anywhere where you have solids that are losing water back to your plant can be flowing back high levels of phosphorus. Generally speaking, if you are adding chemical to something, it's going to be more efficient when there's lots of potential atoms or molecules that you're targeting to react with. So what does this mean? So if you are dosing before final clarifiers, and sorry if you have an SBR here, you're likely having an orthophosphate concentration between maybe 3/4 of a milligram per liter to 5 milligram per liter most of the time. Yeah, every plant will be a little different, but that's a broad range that's pretty reasonable. So relatively low levels. What we're finding when I'm working with plants here in Kansas is that dissolved orthophosphate levels in return flows from solids processing may be anywhere on the low side of maybe 10 milligrams per liter up to greater than 100 milligrams per liter. Translate this into mass, and we're looking at some plants maybe 30, 40, 50% of their entire phosphorus loading is coming from biosolids operations. So if we can reduce that loading, in theory, we should be able to reduce the amount going out of the plant. Additionally, with this higher concentration, that means your metal salt dosing is likely to be more effective because there's just more opportunity to hit a target when there's more targets out there. Most facilities are not tracking orthophosphate coming back from decanting, belt filter press, and things like that. If you are kind of on the borderline for meeting phosphorus limits and goals, I would suggest you begin doing that and determine if this is something you want to try and take action against. Um, so I have a few examples to show you. This is not nearly as common as dosing before the final clarifiers, but I think it is something to consider. The basic theory is to control the phosphorus, keep it in the solids, get it out of your plant as solids rather than returning a sizable fraction back to your plant as dissolved orthophosphate in Sunapee, New Hampshire, and I see that there's New Hampshire people on the call today, so sorry, I'm going to butcher that name. I'll call it Sunapee. Um, they dose polyaluminum chloride to their sludge, and then use an anionic polymer, which is like the opposite charge of what you typically are using at your belt filter press here, to bind the phosphorus as part of dewatering. And they have found this is more economic than dosing before clarifiers, and it is just part of their solids operation. They don't do seasonally, they just do it. Um, Here is where their polyaluminum chloride line dose. So this is the sludge line going to their dewatering device. Here is the dosing line coming in, pressure on that. And then this is the port it comes through. Um, this works really well, and then they add polymer like you do on any other operation. So this is really unchanged on their dewatering. What does this look like here in Kansas? I've worked extensively with Pratt. They have a two-cell SBR over here. These are abandoned trickling filters. Um, these are abandoned clarifiers, but they have rainwater in them. And then this is sludge storage all the way over here on the west side of the facility. Um, they do not digest. So they just belt press and go to landfill. So there's some different management than most plants here in the state have with regards to time under aeration for digestion. They don't have to worry about that. Um, they are kind of right on the line, like on a mass, if they get a mass-based limit, they may or may not meet it. And I definitely don't feel comfortable. I don't think they feel comfortable to say, like, we're good to go. Um, so they're doing a lot of process control testing. They were tracking the phosphorus in the effluent, and they found that it increased in the day and just days following belt filter press runs. And they run the belt filter press once a week on Thursday or Friday, all day. It works well with their other schedule. So like, how can we make this better? Um, they tested adding rare earth salts that we talked about to the sludge storage and found it was very effective. Worked very, very well for them, but they didn't like the price tag if they had to do it all the time. So they were continually monitoring that phosphorus flowing back to their SBRs, ended up with a modified decanting schedule where they don't decant as long as they used to. So they used to maybe decant 7 hours. Now they're only decanting for 4 hours. That means the air is on more, which has additional cost as well. But they end up flowing back about half of the phosphorus they were on a mass basis by changing the decanting. So in order to decant the same amount of fluid, they have to decant more frequently for shorter periods of time. So it's changing their plant workflow there is part of their response here, but. They have people there already. They're able to change that workflow without, adding additional labor costs. So this is maybe a way to go. We'll see how they do in the coming months, but we saw with just BioP. They had I think it was December. Their effluent was like 0.5 milligram per liter of phosphorus. So very, very good result. But like anything, you want to see if that's more the new normal or maybe it's something to keep an eye on. I wanted to talk now and in this with dosing chemical that doesn't actually bind the phosphorus. This is a plant in Wolfboro, New Hampshire. Probably pronounced that wrong as well. It's an old plug flow extended aeration basin. Very well operated, well maintained. Pretty manual operations yet, as far as like control of sludge blanket, return activated sludge, wasting. That tends to be pretty manual. So you have four parallel plug flow basins. I did not mean to do that. Okay. Influent RAS enters on this side, it goes over here, and then there's overflows to two final clarifiers. This is sludge storage. They haul liquid out of the plant. They're doing something really cool I'd never seen before, and I'm happy to get this out. So they have extended aeration. Extended aeration often coincides with relatively poor settling. They cycle their air. They get really good biological phosphorus removal, really good biological nitrogen removal, just through the cycling of air. Very classic nutrient optimization type of effort there. But for the clarifier, they do some really cool things. So as I mentioned, things are pretty manual here. They turn off the RAS, and then they dose polymer at the end of aeration in that overflow going into the clarifier. They allow that blanket to build, and then they waste. So the polymer helps the settling of the solids. And it also helps to get, especially those solids that don't settle well, those filaments that you get in extended aeration plants, to come out of the water and be wasted from the bottom of the clarifier. And they do that. They waste on a manual operation. And then in the sludge storage, they aerate it, and then they add the same polymer about 15 to 30 minutes before decant, give it plenty of time to mix. And then they are able to decant be very, very rapidly. They're able, a lot of you probably decant after 5 hours after the air is off. They're doing it within 30, 40, 50 minutes maybe. So that they don't get that septic condition where you get phosphorus release from your solids back into your liquid stream processing. So I was like, this is really cool. They have really good numbers. I think their phosphorus is averaging about 0.7 without any metal salt dosing. That's really, really good for the type of plant they have. So I've been working with Norton, and I've shown you that photo before, and they were interested in it. They haul liquid sludge so that they don't have any belt filter press, return flows that some facilities would have, but they do decant so that they're hauling less water. They have done pretty extensive testing and have found that as you get later in decanting, meaning more hours from air off, the phosphorus starts to increase in the decant water that's going back to their driver basins. They did some jar testing with the chemical vendor and acquired a polymer, which is similar to what is used in the belt filter press, but is not the same, to rapidly settle prior to decant here in these two digesters. They did this on sludge that was old and, had been in there a long time prior to hauling out to farmland. And they didn't see any changes in total phosphorus from the decant from previous results, which was kind of disappointing. But they didn't give up. So they have some very positive results on new sludge, where it was able to rapidly settle, keep the phosphorus in the sludge. We'll see how this does over time. With that, this is the end of my presentation.